Now, in the last class, we have derived the compound state, and now we shall calculate the energy of the required electron. Energy of the electron. Now, the initial energy of the photon is h nu, and final energy is h nu prime. So, if we subtract h nu prime from h nu, then that will be the energy of the electron. This energy is imparted to the electron, and the electron recoils with this much of energy. Now, to calculate this, we start from this equation. Now, from equation, we have derived the equation that 1 by nu prime minus 1 by nu, that is equal to h by m0 c square into 1 minus cos theta. That is lambda prime c is taken in this side, lambda prime minus delta lambda. This is the equation. Now, therefore, 1 by nu prime equal to 1 by nu plus this equation h by m0 c square. So, we get this equation. So, one can find nu prime from this. What will be nu prime? That is equal to nu m0 c square. Here you get m0 c square plus h nu into 1 minus cos theta. So, nu prime is equal to frequency of the scattered radiation. Nu prime is equal to nu m0 c square by m0 c square plus h nu into 1 minus cos theta. Or it will be written in this form that nu divided by m0 c square is here, you get 1 plus h nu by m0 c square 1 minus cos theta. Or we write nu prime is equal to, it is in this form, that nu divided by 1 plus alpha 1 minus cos theta. When this quantity alpha is equal to this one, h nu by m0 c. So, this is the expression for nu prime. So, the energy of the required electron, W, that is h nu minus h nu prime, h nu minus, substitute the value of nu prime, you get h nu divided by 1 plus alpha 1 minus. So, if you take h nu common, then it is 1 plus 1 by this, therefore you get alpha into 1 minus cos theta divided by this 1 plus alpha into 1 minus. So in terms of initial frequency and the angle of scattering, one can find the energy of the required electron. Now at which angle the electron is required? How to find the angle of required phi? Now to find the angle of recoil phi, the angle of recoil, it is phi. Now from momentum conservation we get two equations. One is mv sin phi, that is h nu prime by c sin theta, and another equation was mv cos phi, is h nu by c minus h nu prime by c cos theta. These two equations we have obtained from the momentum conservation. Now if we divide this one by this, so here we get mv sin phi divided by mv cos phi is equal to h nu prime by c sin theta divided by h nu by c minus h nu prime by c cos. This h by c will cancel. So here you get tan phi nu prime sin theta divided by nu minus nu prime cos theta. Now if we substitute the value of nu prime here, substituting the value of nu prime, nu prime is equal to nu divided by 1 plus alpha into 1 minus cos t. If we substitute this value here, then we get tan phi is equal to nu divided by 1 plus alpha 1 minus cos theta sin theta divided by nu minus nu divided by cos theta cos phi cos theta. this is equal to sin theta divided by 1 plus alpha 1 minus cos theta minus cos theta. Now sin theta, we write it 2 sin theta by 2 cos theta by 2, 2 sin theta cos theta, and this is 1 plus 1 minus cos 2 theta, and we have 2 alpha sin square theta by 2 minus 1 minus 2 sin square theta by 2. Cos 2 theta. And if we evaluate this, this one will cancel, we get, so sin theta by 2 will cancel, then naturally you get tan phi is equal to 1 divided by 1 plus alpha tan theta by 2. This is the relation between the phi and the theta. It is if we know the angle of scattering, you can find the angle of recoil. Now, we know that is theta. Initial direction, the electron is here. This is theta, and this is phi. Now, theta may vary from 0 to 180 because either no scattering, 0, theta is 0, or head-on collision. The photon bounces back from this electron. So theta varies from 0 to 180. Theta varies from 0 to 180 degree. Then what will happen? How the phi will vary? If say theta is equal to 0, theta is equal to 0, this is 0, so phi will be, tan phi will be equal to infinity, so phi will be equal to pi by 2. Tan 0, 0, so you get infinity this side, so phi is 90 degree. And if theta is equal to say 180 degree, pi theta is equal to 180 degree means this is tan 90. So this thing is infinity means 0. So tan phi equal to 0, then in that case phi is equal to 0. So theta varies from 0 to pi, and this phi varies from 0 to pi by 2. So the required electron cannot come in this direction. Either it maximum it comes out of the atom in this direction, in the perpendicular direction to the initial direction of the photon. So theta varies from 0 to 180 degree and phi varies from 0 to pi by 2. Now another process which has just the qualitative idea, not the detailed theories in your course, that is pair production. That is the H nu, the radiation, the energy is completely annihilated and two particles of same mass are created. One is electron and another is positron, positive electron. Suppose this. When the high energetic electromagnetic radiation, that is gamma ray, very high energetic, passes in the vicinity of the nucleus of an atom, then in that case such kind of process takes place. That means the energy is completely annihilated according to Einstein's theory and the particles are created. From that one can say that the energy is nothing but the mass is nothing but the frozen state of energy. Mass is created, energy is completely annihilated. And for this process to take place, the presence of other particles are required, that is the nuclear particles should be there. Now, therefore, in this case, suppose it has the velocity v, so momentum p, it has a momentum p, it has the same momentum p. Now, from conservation of energy, from energy conservation, what we write that H nu, initial energy, is equal to final energy is twice mc square. Both have the same mass. Mass of the electron positrons are same, only the charges are different, plus charge and minus charge. So twice mc square. So initial energy is H nu and final energy is twice mc square. Now, if we use the mass energy relation, therefore you get twice m0 c square into 1 minus c square by c square. So, from momentum conservation, along this direction and perpendicular to this direction, H nu by c, the initial momentum of the photon in this direction, that will be equal to the momentum of this and momentum of this, that is p cos, twice p cos theta. It is twice p cos theta so H nu is equal to twice pc, c is taken in this side, cos theta. So H nu is equal to twice mv. Suppose v is the velocity of this electron and the positron. So p is equal to mv c cos theta. If we substitute the value of m here, so H nu will be equal to twice m0 Vc by 1 minus v square by c square to the power half cos theta. If we write it in this form, twice m0 c square, then here you have to say v by c, it is in this form. Twice m0 c into this, write it twice m0 c square by this cos theta into v by c. Because initially h nu was equal to, from energy conservation, that is twice mc square, twice m0 by 1 minus v square by c square to the power half into c square. So twice m0 c square by this quantity is here. From momentum conservation we write. Now actually cos theta, the value of cos theta we know that it varies from 0 to 1, either less than 0 or equal to 1, and the velocity of the particles created there are less than the velocity of light, because there are no material particles which can move with the velocity of the light. So v is always less than c. So here v by c, this quantity is less than 1. Also this cos theta, this quantity is less or equal to 1. So this quantity, from momentum conservation, we have this quantity is multiplied by two quantities which are less than 1. So therefore this quantity must be greater than this one. So this quantity twice m0 c square by 1 minus v square by c square to the power half is greater than h nu. Now, because in this process the energy conservation is not taking place, h nu is equal to, should be equal to this quantity, but it is observed that this quantity should be greater than 1, because the rest of the, in the two body subsystem mainly, the energy momentum conservation principle does not strictly hold good, because some part of the energy and the momentum are carried away by the spectators, by the other particles which are present in the vicinity. Here the some of the energy and the momentum will be carried out by the nuclear particles, because it is taking place in the vicinity of the strong nuclear field. So therefore we to take the pair production process, because the rest energy of the electron, the rest energy of the electron or the positron, that is m0 c square, it is approximately half MeV, 0.5. So twice m0 c square, it is actually 1.02 MeV. The rest energy of the electron and the positron, twice m0 c square, is of the order of 1.02 MeV. So to create these particles of this much mass or this much rest energy, the incident photon must have energy which is greater than this one. Then only the pair production will take place, otherwise not. If the energy of the incident photon is less than this one, no possibility of pair production. So for pair production process, h nu should be greater than 1.02 MeV. So if a high energetic gamma radiation passes in the vicinity of the nucleus or in the strong nuclear field whose energy is greater than 1.02 MeV, then only the pair production will take place, otherwise not.